Good morning to one and all, and a very warm welcome. I extend my sincere thanks to all the participants out there for sparing their precious time in participating in today's webinar on ARM processors. I, Swati U, Assistant Professor, Department of Information Science and Engineering, VKIT, extend my special welcome to our resource person, Mr. Harish V. Mekali. Welcome, sir.
Thank you, ma'am.
Mr. Harish was born and brought up in Gadag. He's working as an assistant professor in BMSCE from 2010. Currently, he is pursuing PhD from IIT Bombay. His research interest includes embedded systems.
Hello. Hello.
Hello.
Swati?
Hello,
Ah,
can you hear me?
your voice is not audible, Swati.
Am I audible now?
Yeah.
Okay, sorry for the inconvenience. Yeah, heading back to Sir's biodata. So he has fetched more than rupees 24 lakh grants for his IoT projects and robotics lab. He has 17 publications, including 3 patents, 1 copyright, 7 international and 6 national papers. He has taught 17 courses in UG and PG departments of BMSCE. He has delivered more than 50 guest lectures and trained more than 2,500 plus participants, which is a great thing. I feel great to speak about such a person today. Again, I welcome you, sir.
Thank you, ma'am.
Before getting into the today's webinar, let's do a little bit of housekeeping. So, for all the participants out there, if you have any queries during the session, please drop in your questions in the chat.
Hari sir?
Yes, ma'am.
You can start, I think.
Start, ma'am.
Yes, sir. Yeah.
Is my screen is visible, ma'am?
Yes, sir. It is visible.
Very, very good morning to everyone. Ma'am, in case if there is a disturbance or the connection issue, please let me know. I will
Sure,
switch to the
sir.
other.
Yes, sir.
On my phone, like my phone is next to me, you can just text me on the WhatsApp.
Yes, sir. Yes, sir.
Thank you, everyone. Thank you, VKIT, and thank you all the faculties of EC department and all the faculties of VKIT for giving this opportunity. Quickly, we'll start with the session. This session is about introduction to embedded system. How do we, why ARM processors are so widely used, what it makes so special, and we'll start with uh, bits of bits and pieces of embedded system, like a definition of embedded system, and then like what are the very important keywords that are need to be known if I'm going to study an embedded system, and then we'll go to the why ARM processors, and then like we will discuss on the architectures, types of ARM processors, and then like we'll go to the architecture of ARM processor. So this session is planned for around 45 minutes to 50 minutes session. This is a 45 to 50 minute session. You can ask me the question at the end. If there is any doubt, please note it down. I'll just start the presentation. Right. So let's quickly jump into the embedded system in the beginning. Like, what exactly is an embedded system? Uh, Embedded system is a combination of hardware and software. As a person who have studied the embedded system in different courses, embedded system in UG and the PG courses, and also taught them some subjects related to that. Every textbook, every topic in embedded system starts with an example that, like, okay, embedded system is a combination of hardware and software. The best example for embedded system is a washing machine. So every textbook, any example if you take and look into that, any textbook if you take and look into that, any online search if you check, everything says like, okay, the best example for embedded system is washing machine. The washing machine, yeah, we will also start with the same. There are many others, like including our Wi-Fi router is an embedded system. Our mobile phone and the laptop to the desktop, all these are also part of embedded system, but like we can say them as a general purpose embedded system. So mostly when we say an embedded system, it is about uh, a specific application, a very specific application. Wi-Fi router in that context is a best suited example. Washing machine is a best suited example. So we will start with an example of washing machine. What is there in the washing machine as a basic functionality? If you start a washing machine, it has to rotate clockwise 10 times, anti-clockwise 10 times. Let's talk about the old washing machines. The new washing machines have a lot of features. We'll not take that into the discussion at the beginning of the topic. Old washing machine, that's a feature it has. So to rotate this 10 times clockwise and the 10 times anti-clockwise, we need to make sure that like there is a controller which controls the operation of this motor, which is inside the washing machine, which rotates this clockwise and 10 times and anti-clockwise 10 times. Okay. So to do that, for that controller, there will be a small program written on top, which decides the number of rotations. Okay. So we can define an embedded system as a combination of hardware and software. That's a very basic definition of embedded system. In the sense here, what is an hardware for us? A hardware for us is a controller, and the software for us is a which either written in C or assembly, which goes on top and sits with the controller, which decides how many times the motor in the washing machine has to be rotated and in which direction. Okay. So to go in slightly deeper into the hardware, what is a controller? Controller can be said as a combination of ALU, or like I can say microprocessor, plus the RAM, ROM, timer unit, and some protocols, and some IO ports. Okay. So in this controller, it's a combination of processor, RAM, ROM, and some other things. The very important part is a processor. What is a processor? A processor again can be described in terms of a combination of ALU, registers, timer units, decoding units, and some buses. Again, if I take, we'll try to zoom in and see like where exactly this hardware and software get combined. That's our goal right now. So inside a controller, we came to a processor. Inside a processor, we will focus on to the ALU. What is an ALU? ALU is an arithmetic and logical unit. You can say like, we'll just again in the arithmetic and logical unit, we'll focus on the arithmetic unit. only in the arithmetic unit. What's inside that? You can say they'll, like, if it is a 4-bit processor or a 4-bit controller, so that ALU will have, it will take 4 bits at a time, process it, and gives out the result. That means if arithmetic and logical unit, if I focus on arithmetic unit, in that, if there will be a kind of arithmetic is okay. We'll basically look at to the arithmetic part like this. Anything and everything in maths is addition. There is nothing but addition and addition in the maths. Our subtraction operation is addition, division is addition, multiplication is addition, integration is addition, differentiation is addition. Everything is addition fundamentally. One example that I can give you is 3 minus 2, which is subtraction, can be written as 3 plus of minus 2. We're adding a negative number to a positive number. That's a context. So in such a case, if a subtraction is addition, then like we know the multiplication and the division are like next versions of addition and subtraction, and similarly the differentiation and integration. So the fundamentally anything and everything in maths is addition, right? So when it comes to a processor, arithmetic and logic unit, in arithmetic section, fundamentally there will be only an adder in the bottom. We all have studied something like logic design or a digital circuit design in our third semester or in the early engineering years. In there is something called 4-bit full adder. We can imagine something like that arithmetic unit will have this 4-bit full adder inside it. What is there inside the 4-bit full adder? There are 4 full adders next to each other. We can imagine like that. And what is within each full adder? There will be 2 half adders. What is within the 2 half adders? One XOR gate, one AND gate. So to generate the sum and the carry. So that's a fundamental block of our hardware. An XOR gate and the AND gate, which makes a half adder. 2 half adders makes a full adder. A full adder makes a 4-bit. A combination of full adders makes a 4-bit parallel adder. A combination of these can make it as 8-bit, 32-bit, whatever the bit processor that we want. This full adders, a 4-bit full adder, like combination of that, is an integral part of an ALU. ALU is a core part of a processor. Processor becomes a core part of controller. Okay, that's the hardware layer that we should imagine. So fundamentally, there is an XOR gate and the AND gate. Okay. Now, if you remember that we have done one experiment in the logic design or like digital circuits design, that like a adder can be made to perform the subtraction, right? There is a adder come subtractor experiment in the our logic design subject, where which we defined some bit called as an M bit. M is a mode bit. If M bit is 0, the whole parallel adder will act as an adder. If M bit is 1, it acts as a subtractor, right? Subtractor is, as I told you an example, it is nothing but like 3 plus of minus 2, right? 3 plus of minus 2. What it is doing is, it is taking a ones complement of the second number, right? To do this M bit is connected to a input of an XOR gate, wherein which if XOR gate input, one input of an XOR gate is 0, then it passes the another input as it is to the output. If that one input is 1, then it passes the complementary of another input to the output. I'm speaking of 2-bit 2 input XOR gate. When one input is set to 0, it passes the another input directly to the output. If that bit is set to 1, input of an XOR gate is set to 1, it passes the negation of the another input to the output. So with using this phenomena, we can convert XOR gate as a buffer or the NOT. Using this phenomena itself, we will create an adder cum subtractor circuit. So this is all decided by that one bit. We'll call that as mode bit. If the mode bit is 0, whole circuit is acting as an adder. If mode bit is 1, the whole circuit is acting as a subtractor. This is a fundamental experiment which links the hardware to software. Hardware to software. The M bit, that whatever we are saying there, is our operational code. Is our operational code. If M equal to 0, our operation is addition. If M equal to 1, our operation is subtraction. So that forms a fundamental 1-bit opcode. Okay. Similarly, if there is a complex ALU which has multiple bits of mode bits like M, then it creates the multiple opcodes, right? Opcodes are the fundamental units in the software. Using these opcodes, we will define the something called as mnemonic in the assembly level program. From this assembly level program, as and when its program gets complicated, we shifted to the high level program. We have defined this opcode as a symbol there, plus, minus, and or gate, like equal to, something like that. Using all this, we create some function in the high level language. Using these functions, we create a program. Using this program, we create this software. We will say set of programs is a software. So what is that I'm trying to say is, I'll just wind up. I believe like this topic of discussion or conclusion here should give a clarity of the discussion till now. What is that? An embedded system is a combination of hardware and software. In hardware, when I say hardware in embedded system, it is mostly a controller. In the controller, if you go on looking what is inside the controller, we will see a processor, we'll see an ALU, we'll see an adders, and we'll see a half adders, and then we'll see the XOR and the AND gate, using which we can create an adder cum subtractor circuit kind of thing. Similarly, if I look at the software is a combination of programs. A program is a combination of function. Functions are written in the high level language, or it can also be written in the assembly level language called as subroutine. So in context of high level language, if I consider a function will have an instruction inside. Each instruction depends on the opcode that is defined fundamentally. So what is this opcode? An opcode is a one fundamental unit of a software which defines what hardware has to be done, or what function in the hardware has to be executed. So when we say this topic, we should be clear of what are the depths in the software, what are the depths in the hardware, and where it exactly gets connected, right? So this is an important topic. And after these are the that's a definition of embedded system, and this is how we should look at it. And after this, there are two more words that are very important in the embedded system. That is memory. There are many different types of memories in the embedded system. Basically, we divide them into the volatile memory and the non-volatile memory. Non-volatile, we will mostly say it as ROM. Volatile, we will say it as a kind of RAM. So RAM is our volatile memory, ROM is our non-volatile memory. What do you mean by volatile and non-volatile? If I remove the power, the content stored in that memory will go off. It is a volatile memory. If it is a non-volatile memory, the content will still retain even if there is no power supply, right? So the quick example for volatile and non-volatile, volatile RAM, non-volatile ROM. We'll consider that as an example as of now. So the memory is one where in which we store the information. Of course, yes, that's a correct reason. There are different types of memories again in the controller apart from this RAM and the ROM. We can define that. If I consider my computer or my mobile phone, the fundamental memory that we have, or whenever I purchase a mobile, will come in the reverse direction. Let's see. For a computer, I have a hard disk. I can attach a pen drive. I can attach, I can attach a pen drive. There is a hard disk, and then there is a RAM. Then there is a cache memory inside a processor. Then there is a registers inside a processor. Or I can say there is a register inside a processor. Then there is a cache memory onto the chip of a processor or a processor chip. So I can define these 5 types of memories in my computer. What are the 5 types of memory? Register memory, cache memory, RAM memory, hard disk, and pen drive. Just look at this different types of memories. 5 different types of memories. These 5 different types of memories will facilitate in lot in design of a system. Like if I go to a register, they are the highest speed memories that are available in the system, but they are too costly. And check with that's where like the size number of the or like register memory is it's in the very minimal. It's defined in number of bytes. At the end, on other end, if you check with the pen drive, it's a slowest possible memory compared to all these 5. The pen drive is the slowest possible memory, but cost wise it is damn cheap. Okay, hence mostly the pen drives will come in GB. Or hard disk, if you take an external hard disk, then it comes in the TB right now. Okay, so pen drive and external or hard disk will consider. Till hard disk will consider. Okay, done. Hard disk is a huge memory, but it's a slow memory because it's a damn cheap. Registers are super high speed memories, and they are in very small size in our laptops because they are super costly. Okay, so then there is, that's about the memory. Then there is one more term which is very important in embedded system, that is protocol. A protocol, uh, a, by definition of a protocol, it's a set of rules, right? We can say, let's say like we'll take it into a general consideration that what is a protocol. A protocol is a rule that need to be followed. For example, if I have to drive on the streets of India, I should drive on the left side of the road. Okay, if it is on the some other part of the world, then it's on the right side of the world, like this. I'm just saying that's a rule that we follow on the street when we drive on the street. That's a protocol defined by the RTO office. Similarly, we have a protocols in every stage of life or everywhere. In a family, we have a protocol. Mom does this, dad does this. Their responsibilities. Kids does this. Their responsibilities are different. In a school, we have a protocol, like principal does his work, HOD and the professor and the assistant professor. There is like we have heard a lot of many times that like, okay, come through a proper channel, they follow the protocol, something like that. Okay, if there is an organization or if there is a system or if there is a coordination between any 2 entities, there has to be some protocol that need to be followed. Without a protocol, we just cannot communicate. Why I'm saying this is, a language by itself is a protocol. The rules in the language are defined by something called as grammar. Grammar defines the rules for the language, right? Every some predefined meaning. If I'm talking in English, you should have already and have an information about what is the each word meaning and how it is connected using the grammar. So our communication is proper, and our communication can be understood only because like we agree with the common rules of the English grammar and the common rules of a dictionary meaning of these words, right? So that's a generic understanding of the protocol. So what's the point in saying that is, a protocol is required wherever there is a communication between 2 entities. wherever, right? It is similar in electronics also. Okay. The most widely used protocol at present is an internet protocol, IPv4 or IPv6. We name it as exact to name it exactly. It is IP version 4 or IP version 6. Okay. So we also know we also have some other protocols like USB is a protocol using which we connect our mobile to the laptop. So mobile and the laptop exchanges the information, right? So that's based on USB protocol. Then like that, there are a lot of other protocol. Like for example, I'll give one more example. We have an SD card which goes into the mobile. This SD card content is read by the processor and that get displayed on the screen. So the communication between processor and SD card is mostly on some protocol called as SPI, Serial Peripheral Interconnect. Similarly, there are other protocols. I can say I2C is a protocol, inter-integrated communication. CAN is a protocol which is used in automobiles. Wherever we have electronics in automobile, these electronics devices in automobile communicate with each other using a CAN protocol, right? So there are so many protocols in electronics, depending on the application, depending on the context of usage. That's a particular word. Depending on the context of usage, we have so many protocols. Okay. Again, from like we did the hardware from top to bottom, microcontroller to the adder, the XOR gate and the AND gate. Software, we saw it from the programs to the opcodes, the memory from hard disk to the registers. In protocol also, we can classify them based on the distance. As most of you know, it is LAN, WAN, MAN, and the internet. Right? So there is a LAN, there is a WAN, and there is a MAN, and then there is the internet. Local area network, wide area network, the metropolitan area network, and the internet in the large. We'll just speak with respect to the LAN. LAN is mostly about 10 meter to 100 meter range. What if it is below the 10 meters? Then we call it as a PAN, personal area network. What if it is below that 1 meter? We'll call it as an onboard protocol. Onboard protocol. Onboard protocols are something like SPI. I told you, like when SD card is inserted, my processor will read that information. That's kind of onboard protocol. Now, what's within that is an on-chip protocol. If we have studied like 8086 processor, there is an 8086 bus architecture, and the protocol itself is 8086 protocol for on-chip communication of 8086 processor. So generally it is said as an x86 protocol. Like that, for ARM, we have something called as an AMBA, Advanced Microcontroller Bus Architecture. So this is an on-chip protocol. Now look at from the on-chip, on-board, personal area network, LAN, WAN, MAN, and the internet. If the internet has to work properly, that means on-chip protocol should work properly. If the on-chip protocol communication is proper, then your internet data exchange is proper. Okay, so that's the conclusion of this slide. This is called as, like I have named it as an abstraction layers of an embedded system. There's a hardware layer, software layer, and the memory layer, and the protocol layers. Right? I believe like all these layers are clear. Right? Hardware layer, software layer, memory layer, and the protocol layer. Can I just ask organizers, is it audible properly? Is it going on properly? Hello?
ಹಾ ಸರ್ ಒಂದು ನಿಮಿಷ. ಹಲೋ ಸರ್. ಹಾ
ಕರೆಕ್ಟ್ ಆಗಿ ಕೇಳ್ತಾ ಇದಲ್ಲ ಮೇಡಮ್?
ಯಾ ಕೇಳ್ತಾ ಇದೆ ಸರ್. ಕಂಟಿನ್ಯೂ ಮಾಡಿ ಸರ್. ಓಕೆ ಸರ್, ಥ್ಯಾಂಕ್ ಯು.
So that's about an embedded system. I believe like all these four words are clear, and it's the same perspective, and these are very fundamentals. And I believe this sets the context of understanding between you and me. So if you have the more clarity that we have on these 4 words, the more clarity that we'll get on the understanding of the further topics, or like understanding of any textbook or uh, any topic related to embedded system that we want to study. These 4 words are keywords. If we have an understanding of these 4 words from the bottom to the top, then our understanding goes easily. Okay, that's the intention why we took this topic, or why we took this slide. Right. Let's look at the one by one things now. Like, what's a computer architecture? Because this is again forms the fundamental part of any computer, whether the simplest computer for in my view is a calculator, and the most complex computer is our brain. From the calculator to our brain, what is a fundamental architecture which is common in all this is this slide. Everything that we call it as a computer will have something like this. It will have a central processing unit, a memory, and input output device, and of course a clock unit to define the timing for this circuit. We'll come to that. Right? So anything that we call as a computer right now, from a calculator to our brain, will have this 4 fundamental units: central processing unit, memory unit, IO unit, and the clock unit. And these 4 units are connected using something called system bus. Right? What are the system bus? We have a data bus, control bus, and the address bus. So the communication between these blocks is possible because of these buses. Okay. Yeah, we'll come to we'll take one by one part and discuss, which is in context with our discussion today. A central processing unit is mostly like processes the information. That information which is stored in the memory here. Memory is compulsory? It's all started with the von Neumann stored program concept. Otherwise, memory was an optional, which used to be a part of IO unit. Because central processing unit is super high speed in processing the information, whatever we want to process using the central processing unit, we will store that information in the memory. Okay, and whatever we want as an external human beings want to interact with the system, will do that interaction through the input output device. And the clock circuit defines when there has to be a communication, sorry, not when, how much duration has to be the communication between the memory and the CPU, and the memory and the IO, or like IO and directly the central processing unit. Okay, so these are the functional definitions of this block, or like what are the function of this block? These are the functions. What about the buses? Buses, okay, I will just try to give you one generic example. Hope you'll understand with this context. As I told you, like this is a structure which is common from calculator to a human brain, which I consider as like most complicated computer. If there is an event, then you have to react to that event, right? Then this is how the situation works. I'll just give an analogy so that like this becomes clear. Now, like there is an event that like you want to write something on a paper, that you want to write something. Okay, the first thing that goes is a central processing unit, a brain sends an information to the right hand or the left hand, depending on the your comfortability. Right? It chooses the device. A brain chooses the device, a right or left hand. That happens with respect to the address bus. We can consider that as an address bus. So it sends an information to an address of right hand or a left hand. Once the address is sent, that that hand is selected. Then it sends what is that to be written. For example, I want to say hi. Okay, then brain sends a signal. Okay, this is the information to be written. Then like the hand should move in that passion. Then the control bus decides when you start writing and when do you stop writing. Right? Right? Hope this bus understanding is clear with this analogy. Whenever we want to do some action, then we need to have to decide how do we do action, just by speaking or like by hand, by leg, or these are our input output devices, or I can say in particular output devices, right? So it has to select these devices, then it has to send an address. Then what has to be done through this devices, it has to be sent through the data bus. Then like when to start and when to stop is sent on the control bus. To do this, we have a distributed set of neurals network in our body which does this. Okay. Now, what coming to this topic of clock circuit? Every processor and every controller has a clock circuit. Okay. What is this? It defines what's the duration of each operation in the processor or the structure. Okay. So a clock circuit is basically like we say like, okay, we'll start the this today's session at 10:30. How do we know? Like everybody has a watch and we have a common timing based on which we synchronize. So if any event in the processor has to be synchronized, we need some time reference. That is what is this clock. Hope this point is clear now. So job of clock unit is to synchronize the operations. Okay. Now that's about the computer architecture. As I told, this is common from a calculator to a human brain. I believe everyone is clear with this. And the I/O devices are our output devices are our voice or is an output. Hand is an output device, and the leg is an output device. It can be treated like that. All our 5 sensors are input device. You can think like that. Okay, that's an analogy. Okay. Now we'll particularly look into this is a generic computer architecture, and you take any processor on the world or any computer on the world, this is what it follows. Now let's focus on a central processing unit, CPU. Sorry. We will just go to one topic wherein which a broader classification is done, and then we'll come to the what types of CPUs and the types of memories into that. Right. This is again like a classification of microprocessor and controller. If you check the any video question paper, this is a standard 5 marks question paper. Standard 5 marks question. Okay, in the microcontroller or like microprocessor paper. But fundamentally, a processor or a controller is designed by us. Depending on the application, we design like that. For example, like to go to my college, every day I use my 2-wheeler, right? And nobody says like I cannot use a 10-wheel lorry to go to college. We can do that, but it's not designed for that thing. And nobody says that we cannot use the helicopter to go to college. We can use it, but we cannot afford it, right? Similarly, there are some things designed for some application. If the application has an intense processing requirement, then processors are used. If the application has controlling features, demands controlling features in it, then we use a microcontroller. And accordingly, these have been designed. So what's the point in the mentioning this is a microprocessor is for processing application, microcontroller is for controlling application. That's it. Whatever is required for that operation, we include it in one chip and we call that as a microcontroller. Whatever is required for this processing application, we include in one chip, we'll call that as a processing application. Right? So this is a context of application defined terms. Processor is for processing, controller is for controlling. Now, we cannot control something without having a processing information. Like, I need to control something, that means that I need to understand and I need to process the information and then like react onto it, right? So controlling is not possible without processing. Hence, like there will be a small processor within the controller also, right? With this understanding, you can go on the listing out the difference between them, but that's a fundamental understanding. Processor is for processing, controller is for controlling. Now let's look into the types of CPUs. There are two types of CPUs: CISC and the RISC. CISC stands for Complex Instruction Set Computer. RISC stands for Reduced Instruction Set Computer. What's one fundamental difference between RISC and CISC? Yeah, it has, when it is started, it has a clear-cut differentiation. Nowadays, it's all about like utilizing the best of both. We'll come to that point. Whenever I say RISC, the fundamental requirement in RISC is every instruction should be executed in one cycle. Every instruction in RISC has to be executed in one cycle, and mostly it has to be of same length of instruction. In CISC, it can be of different length of instruction and it can execute in one or multiple cycles. So that's a fundamental difference. So RISC is basically all the instruction will execute in the same duration of time and almost of the same length. CISC is different length and different timing to execute. What do you mean by this? Whenever I say reduced instruction set computer, that means we'll quickly jump to the with example. Hope with the example it will give a more clarity. In case of ARM, which is a 32-bit processor, we have around 40 to 50 opcodes. In case of x86 8086, which is a 16-bit processor, we have 500 plus opcodes. Hope this is clear. The number of opcodes defines the type of CPU it has. There are 40 to 50 or like maximum 60 opcodes in the ARM. So that makes it mostly RISC. Actually, ARM stands for Advanced RISC Machine. Right? I just took that as an example of RISC here. We'll discuss what is the advanced part later. So Advanced RISC Machine, RISC in here has 40 to 50 to 60 at the maximum. CISC as an example, the number of opcodes goes up to 500 as an example. When I have more number of opcodes, it is very easy to design a software for it because it understands the more words. So I can write using those words, I can write the software very easily. When RISC understands only like 50 to 60 words, anything that I want to say to it, like I have to tell it only in those 50 to 60 opcodes. Hence, writing a software on a CISC is a very easy job. Writing a software on the RISC is a very tedious job. What do you mean by software here? It starts from assembly language program or an assembler itself or a compiler itself or like any level of program that we want to we can define. So what's the point in saying this is again, in RISC, software is complicated, hardware is simple. In CISC, hardware is complicated, software is simple. What's our choice? Our choice depends on the application again. We cannot say like this is the best, this is best. Both of has its own advantage and disadvantage. We'll take that in our coming session, and we can go through the classification based on this understanding. Okay. Now this slide again says like in CISC, greater complexity at the hardware level, processor level. In RISC, the greater complexity is at the compiler level. Processor hardware is simple here. Okay, right. And then there are two types of memories. There is a von Neumann memory and the Harvard memory. Von Neumann memory has one memory wherein which both the data and instructions are stored together. Hence, the instruction is fetched first, decoded, and then the data is fetched. In the Harvard, data and instructions are fetched together, and because they are stored in separate memories. What is the advantage? Harvard offers an advantage of speed, wherein which von Neumann offers the advantage of space. Again, what is best depends on application. What's your option? You want to compromise on the speed or space? Depends on that. Okay. So again, different ARM, any processor or any controller, if you check, like mostly they will be available with both the version. Von Neumann memory structure, also on the Harvard memory structure. Okay, right. Now, with an understanding of all this, this is all goes to the fundamentals. I think we have taken good time on it. Now we'll come to the point that like, what are the options of microcontroller and processors we have in our market? So these are all like microcontroller suppliers or like processor or like controller suppliers. There's the Natmel, Texas Instrument, NXP, Microchips, Silicon Labs, ST Microcontroller, Renesas, Infineon, Cypress Semiconductor, Panasonic, Samsung, and then Intel. All these guys. There's so many already like microcontroller suppliers in the market or processor suppliers in the market. Why we need to study on the ARM? That's a fundamental question that we need to address, right? So, uh, excuse me, ma'am, like, can I extend it for another 20 minutes? Do I have a time?
Sure, sir. Sure.
Okay,
No problem.
sure. Right. So, with all this understanding of RISC, types of memories, Howard von Neumann, the protocol, memory, hardware, software, what is microcontroller, processor. With this is a basic understanding. Now we'll venture into the part. When there are so many suppliers in the market, why we need to study the ARM processor itself? We have fundamentally like 4-5 reasons. We'll look into that thing. Let's see. ARM is most widely used or came into a limelight, we can say like popularity, only because of portable electronic device popularity. From the time when handheld devices like we had something called Simputer before mobile comes into picture, or we had this idea of laptop making or like mobiles, pager, video games, electronic toys, calculators. All these are part of portable electronic devices. So ARM's major popularity is because of portable electronic device. Whenever we have this electronics which is portable, we need a processor which consumes as low power as possible. Hence, a low power processor becomes very, very important. So ARM is the world's most low power processor that is available at present. Okay. Second point. Smallest size. By the number of gates that uses or number of transistor that this uses, it's smallest compared to a similar performing processor offered by any other company in the market right now. That's the second reason. It's the smallest. Its size in the microcontroller is also same as a real estate business on the Bangalore or in any part of the city. Right? You increase the size, you have to pay more. Okay, and we wish our mobile should be comfortably smaller, right? Hence our processor has to be smaller in that context. Then there is an important part called as like high code density. This is what made ARM unique compared to other low power controllers or processors, other low power processors. Like ARM has this concept called as thumb mode and ARM mode. There are two modes in ARM. Whenever we want to execute a simple operation like addition of two numbers, subtraction of two numbers, very simple operation like AND operation, OR operation, something like that, we can do those things in the thumb mode. Thumb is actually 16-bit mode in ARM. ARM is actually 32-bit mode. That's the analogy again. So if I want to execute a simple operation, I will go to thumb mode, which is 16-bit mode. I can put more instruction of 16-bit in a program instead of using a 32-bit instruction for the same thing. That's where thumb mode became popular. Our thumb mode is a key design feature in ARM, which gave it so much of popularity. Right? If you take any program, the complex operations in that program will be very minimal. There will be 1, 2, or maximum 3 or 4, or like I can say 10% of the program there are complex, or 20% of the program there are complex operations. Most of the programs I'm saying. Remaining 80% of the program, there will be mostly simple operation like fetch the data, store the data, do some simple operation, then like store it back, fetch it to the memory, send it to another memory. All these simple operations are done in 16-bit. Hence, in the memory of 32-bit, I can put more number of instructions, more number of 16-bit instructions. So whenever I require the complex operation, then only I will go with ARM mode. If there is no thumb mode, if there is a 32-bit memory, I were to fit the 32-bit instructions into that memory. Each instruction is 32-bit in that context, whether it is a simple operation or complex operation. The number of instructions will increase greatly. So by introduction of thumb mode, in a given space, you can put more number of instructions. That's what we call it as a code density, a very high code density, right? Next one, very low cost. Why it is low cost? Because of its business model. I think I will take this if the time permits at the end. ARM has a versatile business model. They have a total different business model. We'll come to that in the end of the slide, like end of this presentation, if it times permit. If not, if I don't take up, you can ask that in the question session. We'll answer it there. Then, okay, one more important feature of ARM is easy to debug. What do you mean by debugging? Debugging is finding an error in the program where the error exists. Whenever we code and dump it to the controller, then it starts giving an error. To understand where is an error, I should know what is going on inside a controller. If I know what is going on inside a controller or inside a processor, I can easily say like where is the error in that, right? So what ARM did is they've attached this debugging circuit to a processor directly and made it as an integrated part of processor itself. Okay, so what is the debugging feature in this? Mostly ARM uses a JTAG debugging feature in the initial structure, like ARM 7 TDMI. What is there in our syllabus? It has a JTAG debugging feature. What it does, the JTAG circuit which is sitting next to the processor will scan all the data movement, all the register content before execution of instruction and after execution of instruction, and send it to a computer, to a programmer, right? In which I can say, okay, this is a possible error easily. If there is no such feature, it is very, very, very difficult to find out like where is an exact error in the 10,000 lines of code of program. It is very difficult to find. So ARM integrated this debugging feature to a processor and made it as an integral part of a processor. Okay, these are the 5 key features why ARM is so famous, and ARM has achieved the best results in all of this. It has lowest power, smallest size, highest code density, lowest cost, and very easy to debug feature. These are the 5 reasons why ARM processor is so famous or so widely used in most of the. Again, remember, this is hugely contributed towards portable electronic device. Till today, we rarely use ARM in the desktop computers. Till today, we rarely use ARM in a servers, mainframe computers, right? So mostly ARM is targeted to the portable electronics device. What do you mean by another side? Like there are in the world, there are more number of portable electronic devices than a desktop or a servers or the mainframes. That's where like the popularity of ARM is so much. Okay. Right. So ARM has a 32-bit ALU, 32-bit bus width, 32-bit registers, 32-bit port. ARM is all in 32-bit. All ARM features are all in 32-bit. Okay. Everything in ARM is 32-bit. That's way I can say it on the main section. Hope this point is clear. Again, if there is any doubt, we can always discuss on the question answer session there. Now, understanding with an understanding of why we need to work with ARM processor, or why we need to select an ARM processor for our design or application. Now we'll look into a part that like what are the types of ARM processor that we have. ARM processor that have been designed till now can be classified into 2 types of processors: classical ARM processor, Cortex ARM processors. Classical ARM processors are something like ARM 7, ARM 9, ARM 11. These are the 3 main ARM processors which have got wide popularity in the market. There might be other processors launched by ARM company, but like not got that popular in the market. So ARM 7 is the first processor family from the ARM that got widespread application. Okay, again because of thumb instruction and the debugging feature that they have added. Of course, the low power and the small size and the cost also, but majorly these 2 reasons. ARM 7, 9 and the 11 are like just an increase in the complexity of the basic ARM 7 family. ARM 7 family, like an example I will tell you, ARM 7 family has 3-stage pipeline. ARM 9 family has 5-stage pipeline. ARM 11 family has 7-stage pipeline. It is just an increase in the complexity of the same fundamental architecture. Okay, ARM 7, 9 and 11. Once they came to this point like of designing ARM 11, they understood that there are so many different applications, we cannot fit all the applications or we cannot fulfill all the application requirements using a single processor type. Hence, they have launched 3 category of processors, and then they started saying it as a Cortex family of processors. There is a Cortex M series, R series, and A series. You can see this all marked in red or Cortex A series. They are designed to work with some operating system, and hence they are mostly the part of our mobile. Right, mobile has this Android operating system. Hence, if you check what is the fundamental processor which is there in the mobile, 90% of the mobile, it is mostly an ARM Cortex A series processor. ARM Cortex A series processor, right? Then there's a Cortex R series processor. R series is for time critical applications, or I can say like R stands for real time applications. wherein which A stands for application processor, Cortex application processor, Cortex real-time processor, Cortex microcontroller type processors, or microcontroller processor for microcontroller type of applications. Okay. So Cortex R is widely used in wherever there is a time critical application. For example, I'll just give one quick example. In our flash, whenever we need to capture a photo, if I'm using the flashlight, the flashlight is available only for that small duration, and the image has to be captured exactly in that duration. If it is captured slightly before or after, there is no use of having a flash on a mobile or any camera mobile, I'm saying. So the real time defines a task has to be happened within that time. If there is time crosses, there is no use of it. And these Cortex R series are most widely used in automobile sectors, especially for airbags. If the car has an airbag, then when a car meets with an accident, the airbag has to open in that duration, wherein which the chest should open before a chest should hit the steering because of an accident. That normally, like when we are driving with 100 kilometers per hour, when there is a crash or when there is a crash or an accident, it is our it is high probability that like we will go and hit the steering. A driver will go and hit the steering, especially our driver head or the chest part will crash against the steering. Hence, there will be a airbag inside a steering which will blow up, and then like it gives a cushion effect between the steering and the chest on the face of the driver. So that airbag has to open in that short duration. If it does not open in that short duration, it opens slightly before or after that, it's of no use. These are very, very time critical applications. So for that kind of application, Cortex R series processors are defined or designed. Then there is something called like microcontroller based processors, or like I can say like processor designed for microcontroller applications. Those are called as Cortex M series. In here, like time is slightly plus or minus time is okay. And these are mostly used wherein which to develop a home automation. If I just come inside a room or inside a classroom, the light should go off, the presenter, like the projector should turn on, the screen should come down, and all this it should monitor the temperature, turn on the fan in or the AC in particular temperature. If it has to be happen, all these things has to happen. We need to monitor the entry and the exit of the people, and monitor the temperature, control the fan, control the lights. These kind of applications, Cortex M series are used. So in ARM processor family, there is a classical processor and the Cortex series. In classical, there is an 7, ARM 7, 9 and 11. After that, they have classified the processor based on the application criteria or application requirement. Cortex M series, R series and A series. A series, example mobile. R series, go with example of real-time application like airbag or a flash of a camera, or like the camera in the mobile. The M series is for like some controlling application that like kind of home automation thing that I have just mentioned. Okay, so these are the types of ARM processor families. Okay, now this is an again slide that requires slightly when we go in depth. I'll just mention a word about it and go to the next one. ARM processor 7 and 9 are called as family of processors. They have a common architecture called as ARM processor architecture 4T. 4T stands for thumb, right? Architecture version 4, wherein which 7 architecture version 7 is wherein in that architecture version 7 they have defined a Cortex series of processors. Till the architecture version 7 they have defined only like classical processors. 4, 5, version 4, 5 and 6 are all classical processors. Okay, so just to give you a clarification, ARM 7 and 9, this is the best easy example to understand. ARM 7 and 9 are different family of processors in ARM, but they have a common architecture version called as 4T. Architecture version is common, but complexity is different. Okay, done. With that, okay, this is one important slide again. This is why there is a one more important part of ARM as compared to a software designer. For example, if I'm designing my software and I've used an ARM Cortex M0 family, example I'm just taking, Cortex M0 family of processor, because I felt that processor ability, which is small, simple and low cost, I felt that like it will fulfill my requirement, I used it. This is the example scenario I'm taking. And then like as I go on designing, like my application went on increased with the increased complexity. Then like I have shifted to the Cortex M3 series of processors. When I shift from M0 to M3, I don't need to change the code. The code that is working on M0 and M1 will also work on M3. Then again, if I shift it to M4 or M4 with floating point unit, the highest complexity of right now, when I made this slide, Cortex M4 with floating point unit was a complex microcontroller that was available. If I shift from Cortex M0 to any of this higher series, I don't need to make a change because the instruction set, the opcode set of Cortex M0 or M1 is a subset of the Cortex M3. M3 opcodes are subsets of M4. M4 opcodes are subset of M4 floating point unit controller. So what it means is, though I can change the complexity of the processor, I don't need to change the software part of it. Mostly it remains same. Right? This is called an upward compatibility. This is a very important part in case when it comes to the design and applications. Okay. Right. Now we'll hit to a point that like, okay, what exactly is an ARM based microcontroller or a processor looks like? Before going to this slide, let me be very, very clear. ARM has not fabricated or manufactured not even a single processor till today. It is a processor design company which supplies a design to other companies like Samsung, Panasonic, NXP, Texas, Cypress. So these guys will manufacture a processor, my controller, and send it in the market. So ARM basically supplies the processor to them. Hence, if you look at ARM-based controller in the market or ARM-based, I can say like SoCs in the market. SoC stands for system on chip in the market. It has similar architecture or similar structure. This is an ARM processor which is attached with the debugging feature. I have already told you why is this and what is this, right? With this ARM processor core, they have attached AMBA AXI. This is an AMBA AXI, which is a high-speed bus. From here, it goes to the APB bridge. This is connection to the low-speed bus AMBA APB. AMBA stands for, as I told you, AMBA is a ARM on-chip protocol. Okay. APB stands for Advanced Peripheral Bus. So this is a slow speed bus. We will just say APB is a slow speed bus, AXI is a high speed bus. That means if there are devices, or like if there are units that operates in the higher speed, we can connect it to the AXI. If there are units which are operating at the lower speed, we can connect it to APB. So ARM provides two types of on-chip buses, AXI and APB. And communication between these two types of buses will happen through this APB bridge. Okay. For example, if it is a memory like a RAM, extra RAM need to be added, flash memory or a pen drive need to be added to this processor, then it gets connected to the AXI bus. See to this. This is a flash drive or SD-RAM gets connected to the AXI bus. From AXI bus, it goes to the ARM processor. This is one. The other side, if I want to add something like a counter, or I can say a TV remote, or I can say a motor control, or a temperature sensor, something like that. These are considered to be slow devices. These can be added to a custom peripheral here. Here I can add a sensor, I can add a counter, I can add a remote receiver. That gets connected to APB through the APB bridge, it connects to the AXI, through AXI it goes to the ARM processor. Data from temperature sensor goes like this inside a ARM processor. Okay, so what ARM offers to these guys or these manufacturer like fabricator is that okay, it offers this ARM processor core with these two buses. It is depending on application that how much of RAM, flash memory need to be interfaced to this, how much of ADC or a counter need to be interfaced to this custom peripherals. So custom peripherals are decided by the manufacturers. ARM offers processor core with this bus structure. Okay, so that's the ARM architecture, which is used in almost all the mobiles right now. It follows the same thing. ARM provides this processor core with the bus. Qualcomm interfaces these models, which are in the shown in the orange color and the pink color. Like it's a Qualcomm responsibility. Launch it as a Snapdragon, which goes into this mobile. So Qualcomm designs this Snapdragon chip. Inside that chip, there is an ARM core provided by an ARM company. Right? So in any processor or a controller that presently exists on the earth, they use a similar architecture. Okay, right. So with that, I just wanted to conclude. Ma'am, we are done with the time. Hello.
Yeah, sir.
Yes, ma'am. So I'm done with the topic. This is just an introduction. Like, why do we use ARM and the types of ARM, and like what is the ARM-based SoC looks like. Okay, and I just have
Yes.
some of the references to be mentioned. I'll just mention and then like opens for the questions.
Okay, sir.
Some
Sure, sir.
references
Sure, sir.
are like there is a video lecture series available by Chris Shore. Chris Shore is an ARM training manager from the ARM University program. That's a YouTube link for. It's available on the YouTube. You can go and search for Chris Shore ARM videos. You will get it. There is a professor from IIT Bombay called as Dr. Santanu Chowdhury. His video lecture series are also available on the YouTube. You can also access them. Also, my lecture videos are available on NPTEL VTU's learning content. You can access it from there. And there are I got all this information from infocenter.arm.com. That has a huge information, right? And the textbooks, Andrew Sloss is a well-known author in the ARM. So his textbook called as by title ARM's System Developers Guide is very famous. Steve Ferber is actually an ARM employee. Another textbook author, Steve Ferber, is actually one of the ARM initial designer, and his textbook is also quite famous, ARM System on Chip Architecture. These are the two very widely used books throughout the world. And yeah, this is a Joseph Yu ARM Cortex M3. This is not concerned with ARM 7, but if it is concerned with ARM Cortex M3 architecture in particular, so we can refer it in that context. Okay, so these are the some references from where I collected all the information. You can also directly go here and get a further information. I should be thankful to ARM and ARM University program in particular for supporting me in all this direction. Most of the materials, most of the controllers that they have given me has helped a lot. I have set up a lab with help of them. They gave us around 100 controllers free of cost. And it has a policy in the ARM University program. I'm just with this thing. I'm just uh, asking everyone to utilize it. You can go to the ARM website and the ARM University program in particular. They have the ARM University program supporting packages where we can register and we can get the some controller boards to work on. Okay. Right. With that, I'm thanks to the VKIT, thanks to all the faculties of VKIT who have given me this option or opportunity to present. Hope it is useful. If there is any question, please ask. I will just open a question answer session with this.
Thank you, sir. It was a way informative session. We have few queries that was put up in the chat box. I'll be asking you that. The
Sure.
first question was one of the participant asked, could you just tell us about the swap instruction in ARM? How can it be coded?
Oh, okay. This section was an introduction to the ARM to explain any instruction in detail like that. We need to understand the processor architecture, very particular processor architecture.
Okay.
Uh, without understanding an architecture, we cannot. It's very difficult to explain the swap or any instruction encoding feature. That's
Okay.
anyway. One thing I can do is like if you send me, this is my uh, website and this is my YouTube link. You can just refer to any one of this. If you send me a mail, I have a content on this. All the instructions of ARM 7 and ARM Cortex M3. I have made a detailed notes. I can share with you. If you still have a question, you can ask me based on that.
Okay. Okay. Thank you, sir. The
Thank you.
next question was, what is pipeline bubble in ARM?
Pipeline bubble.
Yeah.
Pipeline bubble. To be frank, like I don't know exactly like what is a pipeline bubble. There are two important concepts in the uh, pipelining structure of any processor. One is pipeline stall, another is pipeline flush. Stall is somewhere where
Okay.
in which we have a different length of instruction. The one instruction gets added with some duration of extra time, where in which it has to wait for that duration simply. Maybe that is called as a pipeline bubble. I'm not sure with that exactly.
Okay, okay, thank you, sir. And so, like, we have when it comes to the job opportunities, like we have for process application engineer or an embedded engineer, one of
Yeah.
the main skills they look forward for is an ARM. Yeah.
Yes.
So, what do what are the requirements when it comes to an industry side, when it comes to an ARM?
Okay, that's again a more generic question. Like if you take an example in Bangalore itself, we have
Okay.
microchip, Atmel and microchip. They are same now. NXP and Bosch. Bosch uses a lot of ARM-based processor. TI is there. Texas Instruments, Cypress Semiconductor, LG is there. Uh, Qualcomm. All these companies are there in Bangalore, and including ARM. company is there in Bangalore. They mostly do work on two things. When I spoke to them, they mostly work on the two things. One, they companies like Bosch, LG, and Qualcomm, they develop applications using ARM boards. Hence, they do develop a device drivers for it. Device drivers is something like you understand how the ADC works or how the USB protocol on ARM works, and then you write libraries for it. So that's the fundamental job that when I spoke to an LG guys, I understood that way, and also the Qualcomm and the Bosch. On other side, companies like Texas Instrument and uh, Cypress and Microchip, Samsung to an extent, Samsung, these guys work on silicon. I mean, like a VLSI part of an ARM. They take the ARM processor from the ARM company. They try to integrate a memory to it or external protocol to it. So that's basically they work on the VLSI part of it, right? Both these job options are there in Bangalore and also throughout the world. Like of course throughout the world, but they're also in the Bangalore. So VLSI side is also there. The device driver side is also there. To connect to our academics, we need to be thorough with our if you are using a C programming for a keel, we need to be thorough with that, using which we can develop a device drivers. If you are using a Cadence tools or Synopsys tools, you need to be thorough with that to go towards a VLSI design in the ARM processor field.
Okay. Yeah. Thank you, sir. And one more question. What
Sure.
are thumb instructions?
Okay. Thumb instruction is a 16. You can say like if there is an operation just to copy content data from a memory to register, this is a simple operation, right? To do this, a 16-bit instruction is defined, and this 16-bit instruction, to do this kind of operation, 16-bit instructions are defined. These 16-bit set instructions together, we call it as a thumb instructions. These are separate set of instruction in ARM, when which compared to the 32-bit instructions in ARM called as an ARM instruction. So ARM itself has two types of instructions, supports two types of instructions, thumb instruction and ARM instruction. Okay, thumb is basically for doing a simple job, on and off this thing. You need ARM usage, then like you need to have a heavy job.
Okay. What are the advantages of thumb mode of ARM?
Yeah, I just mentioned that in context with code density. You can put if imagine if there is no thumb instructions at all instructions in ARM is 32-bit, and we have 100 memory locations to write a program. Then you can fit a small program into that, or small logic into that 100 memory locations using 32-bit instructions, right? That's I have told you again. I have told you before also, because if we take any program, there will be 80% of simple operation and 20% of complicated operations, right? Even for simple operation, if we use 32-bit instruction, we can fix a limited number of instruction in 100 memory locations. Similarly, if I take, let's imagine now like thumb instructions are there to do a simple operation, then I can fix more number of instructions in that 100 memory location. Hence my logic that I can write a code with the logic, that logic can be extended, the program can be extended. In other words, I can pack more number of instructions in a smaller memory using thumb instructions. So hence thumb contributes greatly towards high code density. Given memory, more logic, then like thumb is supports that in a greater extent.
Okay. The last question, sir. What is the cost of ARM and microcontrollers?
Cost, yeah, cost. It's very difficult to say because there are like it depends on the types of processor and quantity and all that. I heard, and I studied it on the this thing that like ARM lowest possible uh, processor or base ARM based controller is of sub dollar. I can say like around 100 to 70 to 100 rupees. That's the cheapest
Okay.
one. Like it goes on with the complexity and with the quantity, it goes on. And then again, like it is different from ARM processor to ARM based controller. ARM based controller, I'm saying cost from 60 or 70 to 100 rupees. Cheapest one.
Okay, okay. So I think there were only these many questions in the chat box, sir. I would like
Yeah.
to extend my sincere thanks once again for being a
Thank you.
part of this webinar. And we look
Thank you.
forward for more and more sessions from your side. Thank you, sir.
Sure.
Yeah, I
Thank
would
you.
like to thank. Yes, sir.
If to just to mention it again, ARM University program has a lot of supporting tools, and also they have a big team working behind this ARM University program. Anybody from academics can contact them. Anybody. I'm not saying like I'm different from you. Like anybody from academics can contact them. They will support you in all direction. They have a huge resource in terms of materials, in terms of materials in the sense they will send you a hardware board to work on. I'm saying the hardware material itself, and they have also a study material, right? We can directly
Okay.
get in touch with ARM University program. That they have a very good supporting system. Of course,
Okay,
you can
okay.
contact me. Like I have also been doing this kind of workshops. I can share my email ID on the screen. You can contact me through that mail ID also.
Yeah. Yeah. So for all the participants out there, I think if they have more queries, I think you can contact sir with the details displayed on the screen. I would like to even extend my sincere thanks to Janata Education Society, our beloved principal, Dr. Kumar Kenchegowda, our beloved vice principal, Dr. D.V. Chandrasekhar, and our head of the department, Dr. N.P. Netravati ma'am, for their continuous support, without whom this webinar wouldn't be successful. Thank you all. I would also like to extend my thanks to all the faculties who have been part of this event. Thank you. And finally, I would like to thank all the participants for sparing their precious time and being a part of this webinar. So please stay tuned for further webinars from this channel. And if you have any queries, please do contact Sir with the details which is given. The website link, the YouTube link, as well as his personal mail ID is being provided. So please make maximum use out of it. I would again like to thank you, sir. It was a way informative session.
Thank you.
Looking forward for more sessions from your side. Thank you.
Thank
So the feedback link for the particular session will be mailed to your registered mail IDs. So please drop in your genuine feedback and stay tuned for the further webinars. Thank you.
Thank you.